0 part of the axis. That's a musical note. Pick a frequency, let's say 400 hertz, which happens to be A above metal C, and like everything else that oscillates, goes from a high energy to a low energy to a high energy back and forth. There's two things exchanging energy back and forth, like a capacitor and an inductor that are perfectly out of phase. The current goes this way and it goes that way. And there's some kind of external voltage source out here to stimulate it to do that. Actually what there is, let's not get too deeply into oscillators yet. I will get to that before the evening's over. There's something here that will keep that process going forever. It will pump energy into it. It's actually an amplifier where the output's fed back to the input. That's how it really works. But this is the tuned circuit. It's adjustable. One of these things can be varied so that you pick the frequency that you want it to oscillate at. All right, that's the local oscillator. The low frequency component, the audio. That's your voice. That's the part you want to put on the air. What about the thing that is the air itself, the radio frequency? Well, sort of like I described with the Morse code. It's going to be oscillating many times that rate. So I said 400 hertz here. Let's just say it's 1 megahertz here. 1 million cycles per second. Now, the trick is to get this guy and this guy to marry up so that what's here is going to contain the information that's there. How do you do that? Well, what did we do here? We switched using a telegraph key. We turned on and we turned off the radio signal. So what we need to do is something similar with the radio signal here. We have to turn it on or turn it off. Well, it's not a complete turn on and turn off. This thing starts out at 0 and it sort of turns on and it grows until it gets to some positive maximum, goes back to 0, and then it turns on and gradually increases until it gets to some negative maximum. So it's not quite turning on, turning off. It's going up, it's going down, and when it gets down back to 0, it is off, and then it's going up and it's going down in a negative direction. So you're going to be doing something to the features of this radio signal in correspondence with the audio signal. And what you're going to be doing is you're going to be changing the feature called amplitude. To use the first way it was ever done. A-M-P-L-I-T-U-T-E. Sometimes when you're close to the board, you forget what you put down. You can't spell as easily as you can when you're setting. Okay. I want to amplitude modulate this. Just used an interesting word, didn't I? Amplitude modulator, amplitude modulation, which is what AM in the AM radio broadcast band is all about. How does that work? We have a thing, so there's several ways to do it, but most typically, your audio is going to go in here, and it's going to feed a transformer, and then there's going to be another transformer here that's fed from another source. It's going to have this is the audio frequency. This is going to have the radio frequency. And this is going to be modified by this so that what comes out of here is actually something that has a little bit of both in it. And here's what it's going to look like. It's going to look like this in its own funny way. Here's your audio frequency. Remember what we had with the telegraph key? It went both ways. Why? Because the radio signal goes both ways. It's symmetrical, and here's your radio signal. It's actually contained, not really contained so much as its amplitude will vary in correspondence with the amplitude of the audio signal. This thing out here is called an envelope. It's really not there, meaning there's no hard surface, but there's a dimension, there's a limit to which the amplitude will achieve that corresponds to what the audio is at a given moment. So what you have here is your audio symmetrically will let the radio signal expand and contract, and basically you will change the amplitude in correspondence with the audio. You will change the amplitude, you will modulate the amplitude of the radio signal in correspondence with the audio signal. I said the word modulate. And I'm going to make a very simple, I'm going to make a very big deal out of this because the word modulate has been so badly misused or differently used over the years. When citizens band radios were a big deal, in the 70s, I guess 76 was the biggest year for them. That's when they switched from 23 to 40 channels because it got so popular. And it all started in the 1974 era, after the 73 Yom Kippur War in the Middle East. There was an oil embargo. When there was an oil embargo, the speed limits got lowered to 55, and people on the highway didn't want to go 55, so what they do, they figured out somebody that knew where the Smoky Bears were hanging out, and those were the truckers, because they were talking to each other using these things called citizens band radios, and citizens band radios were things that if people could listen in, I would help them figure out where they could speed, where they could get away with it. And as a result, trying to figure out where I was going to go with this. Oh yeah, as a result of this, fancier and fancier CB radios came out. Some of them had a pre-amplified mic with some wave shaping software that would kind of pre-emphasize certain parts of your voice spectrum. And they refer to those loosely as a modulated mic. It's not a modulated mic, it's a mic with a preamp and a filtering circuit to do some shaping of your voice pattern. Also, I heard these CBers talking to each other saying good modulating with you. That's not so improper because every time they speak into the mic, they're applying amplitude modulation to the radio signal, so therefore, I guess they are modulating, but that's not what they're really doing. They're speaking, the radio's doing the modulating circuitry. People who broadcast for very erudite radio stations like WFMT have these well-modulated voices. What does that mean? That means they can control their pitch and their range so they sound equally alike. You can't tell Mace Rosenstein from Marty Robinson or any of the other guys very easily because they all sound the same, because they have the same characteristics. They all have well-modulated voices. That's not really what modulation is. When you hear the word modulation in our context of radio, think of one of many words I'm going to throw out to you. Switching. You are switching with that telegraph key the radio signal on and off. You are switching with your audio this radio signal on and off. You're just not snap turning it on, snap turning it off. You're gradually letting it build up. You're gradually letting it come down. But you are switching it because you are turning it on or turning it up and turning it down. You're mixing. This is probably the best example of what it really is. You're mixing because you're combining this guy and this guy to produce that guy. You're blending them, but you're really mixing because you're doing something mathematical. You're multiplying. Mixing is multiplying. There are mixers inside radio circuits that do what super heterodyne radio circuits need them to do. You are literally number of cycles per second here and the number of cycles per second here, and you're doing a little bit of mathematical operation called multiplication. There are a few other words that I would use, I just can't think of them at the moment. Another one is heterodyny. Another one is a beat. You may have heard of a beat note where you actually hear in audio circuits they call this a wow, where the amplitude of two signals that are close in frequency together tend to produce a wow, wow, wow kind of effect. If you play guitar, you know that every string is, 6 frets separated from the one for it. So what you do is you hold your finger on the 6th fret and you tune the next string to be that frequency. And if the two are just a little bit off, you hear this flutter in the amplitude because the two signals are just a few hertz apart and they actually interfere with each other. They actually add and subtract from each other depending on whether their crests coincide or are in opposite directions at the given moment. Those are mechanical waves. When you have sound, you have a wave. When you have a wave, you have something that does this. It oscillates, it goes up and down. If it's a shorter wavelength, the oscillation gets quicker. That's part of this process we talked about where you have wavelengths and you have pitch or frequency, working sort of in opposite ways. I mean, those are some. I could probably come up with a couple of others if I put some thought to it, but they're all the same process, but those are used interchangeably to mean exactly the same thing. You're multiplying these signals together. What you are doing is using the formal description of an oscillating signal, which is that its amplitude is whatever that, let me put it this way, yeah. Why don't you use a different letter up in front? Kind of thinking about this as I go along. You want to have a voltage that's equal to that maximum amplitude, whatever that A level is there, times the sine of omega t. Omega is the circular frequency. Frequency is the rate at which this thing goes around the circle. Now the frequency is the inverse of time. It's the number of times you make that trip in a given period. So it's cycles per second. Because of what I described earlier, you have a radius here and you have a diameter here and you got a circumference here, and the circumference is equal to pi times the diameter, which means it's 2 pi times the radius. Make that a capital R. In mathematics, we talk about how many radii we go through here. Well, the circumference is 2 radii we go for every frequency rotation. 2 radians, and therefore omega is 2 pi times the frequency. It's the number of radians per second times the time, and that's just the way engineers like to express it for good reasons. It helps them compute many things. Okay. We got our audio voltage here. We have our radio voltage here, and there'll be two different frequencies multiplied together. Instead of just saying sine omega t, I'm just going to say sine of A and sine of B. And what's going to happen when I multiply these guys together, this guy times that guy, sine of A times sine of B is going to be equal to the sine of A plus B plus the sine of A minus B. Sum in the difference. Is that important to us? It'll help your thinking a lot when I show you what happens when you do this thing called amplitude modulation. Stuff I'm giving you now is not in the book. This is what is the concept that makes this whole business of modulation understandable. The book will just say, okay, got a thing called a modulator, we're going to put this audio in one direction and the radio signal in another direction, and out pops AM. We'll never tell you how it works, but I will. This is a frequency plot. This is time. When you have a pure sine wave, if you sort of look at it from the edge, on a frequency diagram it's only one place. If it only operates at one frequency, it only has this kind of a profile. An instrument called an oscilloscope will give you this kind of a picture of that wave signal. I mentioned that last week. Another instrument called a spectrum analyzer will give you this kind of a profile. One will have frequency as the horizontal axis, one will have time as the horizontal axis. Both will have amplitude as the vertical axis. So you're going to look at one according to time passing by. You're going to look at the other in a profile like a radio, like the radio dial, where you have this. Remember the old days when radio had the slide rule thing that slid back and forth? That's what you got here. A spectrum analyzer is really a radio receiver where you can actually see the radio signals. Rather than listening to them, you look at them.